Patty's Calculus Videos, written and performed by me, Patty Leitner.
Part 2, Derivatives. Section 2.8, Rates of Change and Differentiability.
Lesson 3, a logic lesson, and graphing f prime from the graph of f. And that turns out to be true in general if the function is not continuous at a particular x value, then it is not differentiable at that x value. The limit as h goes to 0 of our expression f of x plus h minus f of x divided by h simply does not exist. Well, let's try to summarize what we've said so far and summarize when f prime of x fails to exist or is undefined is another way to say it at a point x equal a, and it will fail to exist if, and the first thing we said is if there is a cusp or corner at x equal a. The second place we talked about is if there is a vertical tangent line. So the tangent line exists, but unfortunately remember that the slope of the tangent line is undefined, and it's the slope of the tangent line that's equal to the derivative, so the derivative will be undefined. And the last one we talked about, we saw several different examples, but in general, whenever f is not continuous. So f prime of x fails to exist at a point A if any of these things happen on the graph of our original function f, the graph of f. So I'll say if the graph of f has a cusp or corner, has a vertical tangent line, or is not continuous at x equal a, then we're in trouble and f prime of a does not exist. Okay, so next we're going to take a side excursion into logic, and we're going to learn a little logic lesson, and it will help us to state a theorem that has to do with this statement number 3 that's down here, where if the function has a point where it's not continuous, it turns out that that function is also not differentiable there. But to understand that, we have to understand a little bit about logic. In logic, we often have things like this. Capital A implies capital B. So this double arrow here really means the word implies. And A and B are statements. So if statement A is true, it automatically implies statement B is true. And if A implies B, if one statement implies another, then what's called the contrapositive of that statement also holds. The contrapositive of the statement A implies B is the opposite of B. We'll call that not B has to imply not A. Well, what does all this mean? It just probably sounds like gobbledygook if you don't have a specific example in mind. So here's an example. And this particular example is the one that I use in my class at DVC, which is Diablo Valley College. So pretend for a moment that you are a person in my class at Diablo Valley College, and you say to yourself, I'm in this class. That implies the truth of this statement, I'm a Diablo Valley College student. And that makes sense. If you're in a Diablo Valley class, you must be a Diablo Valley student. Now, I put a little note in here in parentheses. Does this mean the negation also holds? The negation is actually different from the contrapositive. The negation simply says not A implies not B. The negation of this statement would be I'm not in this class, in this calculus class, implies I'm not a DVC student. And notice that would not necessarily be true. Just because you're not in my calculus class doesn't mean you're not a Diablo Valley College student. You might be in an art class or something like that. So this is not correct. the negation does not necessarily hold. But the contrapositive should hold. So what I'm going to do is the contrapositive. This is my statement A, and this is my statement B. And what the contrapositive should be is not B should imply not A. So you take the opposite of both statements and you turn the order around. Well, here's B. I'm a DVC student. Let's write the opposite of that. So I'm not a DVC student, not a DVC student. And would that imply that you are not in this class? I'm not in this class. That would be correct. If you're not a DVC student, you can't be in a DVC class. So when A implies B, the contrapositive always holds. Not B will always imply not A. Now, remember, we had this statement down here in part 3. We said f prime fails to exist. In other words, the function is not differentiable when it is not continuous. And I've written the statement out in the opposite order just to kind of make it flow a little better. Whenever f is not continuous, then f is not differentiable. We said f prime fails to exist if our function is not continuous. I'm going to skip the negation here, so I'm just going to cross those words out. Let's go ahead and try to write the contrapositive of this statement. Here's my statement A. At any point where my function is not continuous, it is not differentiable. That's my statement B. And really, these are already written sort of as nots. So now the contrapositive, what I want to do is take the opposite of B. In other words, I'm looking at a function that is differentiable at a particular point. That would imply that f, I want not A here. A is a statement that f is not continuous at a point, so the opposite of that, not A, would be f is continuous at a particular point. And this turns out to be a rather important statement. If f is differentiable at some point x equal a, it implies that f is automatically continuous at that value x equal a. And that turns out to be fairly important. So up here we said that if f is not continuous, it means f prime fails to exist. In other words, f is not differentiable. And the contrapositive of that statement would be if f is differentiable, then f is automatically continuous. And that just turns out to be a useful fact. Anytime we know that a function is differentiable, we will automatically know that it is also continuous at such a point. Well, let's go ahead and turn to the next page. So what I thought we would do on this page is look at the statement that we had at the end of the last page. We said that if f is differentiable at a value x equal a, then f is automatically continuous at x equal a. And what I'd like us to do just as practice in doing proofs is to prove this statement formally. We've given an argument for it with pictures and things like that. We argued that if f wasn't continuous at a, then it wasn't differentiable at a. And then we knew from logic that the contrapositive had to be true, and the contrapositive is exactly this statement. But we didn't prove it formally, and we will use this so often that I thought it would be nice to do a formal, precise mathematical proof of this. Well, anytime you're doing a proof, there is always some information that is given, and there is some information that you are asked to show. So let's see if we can pick out what the given is in this case, and then we'll try to figure out what it is we are asked to show. Well, what are we told? We're told f is differentiable at a, and as long as that's true, then the rest of this stuff is supposed to be true. So the given information is that f is differentiable at x equal a. Well, what are we asked to show? We're asked to show the conclusion of the theorem. So the conclusion of the theorem is right here. Maybe I should underline the conclusion is right here. We're asked to show that f is continuous at a. So we're asked to show f is continuous at x equal a. So now we've at least identified if we're given that if f is differentiable at a, then we're supposed to show the conclusion f is continuous at a. Well, when we're given some information like f is differentiable at a, we want to ask ourselves, what does this mean? So what does it mean? Let's see if we can figure that out. Let me do that in a different color underneath here. Saying that f is differentiable at a, remember what that means is that that limit as h approaches 0 of f of a plus h minus f of a over h, it means that limit exists. It means f prime of a, which is that long limit as h approaches 0 of f of a plus h minus f of a, all divided by h. It means that limit exists. Okay? And the thing we're asked to show is that f is continuous at a. Well, what does it mean to say f is continuous at a? If we go back to our precise definition of continuity, there were really those three conditions that had to hold at x equal a. But I'm going to write down the shorthand condensed version of our precise definition. You might remember it means that the limit as x approaches a of f of x has to exist. That was, I think, condition 2. And it has to be the same as f evaluated at a. This expression has to be defined and has to equal the limit as x approaches a of f of x. So whatever f is getting closer and closer to as x approaches a has to equal or match the value of the function when you plug a in. So that's what each of those two things mean. Well, how can we use this thing to show this thing? So that's sort of our next question, is how can we use the fact that this limit exists to show that this other limit as x approaches a of f of x is equal to f of a? So let's see if we can do that. And what I want us to do is take the limit that we know and try to get from it this other statement that includes a limit out of that. And it might be hard to see how to do that at first, but just see if you can follow the steps in the logic as we go through it. So we know that this limit exists, and what I want you to do is think a little bit about what's happening in the top and the bottom of this expression as h gets closer and closer to 0. The bottom of this fraction has to be going to 0. We know that because h is approaching 0. We also know that this limit exists. Suppose for a moment that the top went to something that was non-zero. Maybe the top is getting closer and closer to 5, or just any number that is not equal to 0. If that were true, if the top were approaching, say, 5, and the bottom were approaching 0, we would actually be in trouble. You would have 5 over something that is getting smaller and smaller, at least in absolute value. And you might remember that a tiny denominator makes a big fraction. So if the top were going to something that isn't 0, while the bottom went to 0, it would mean that our whole limit was going to either a plus or a minus infinity. And remember, plus or minus infinity, if our limit is going to positive infinity or negative infinity, that's actually a special way of saying the limit does not exist. So we would be saying that we were in this situation where the limit does not exist. But we are told that f is differentiable at x equal a, and we said that means that this limit does exist. So this scenario that I made you think about can't possibly happen. We know the bottom is approaching 0. The top cannot be approaching something that is non-zero, because if it is, we get into this situation we discussed here, and the limit would not exist. We know the limit does exist, therefore the numerator of this fraction must be approaching 0. It's the only way the limit could exist. This would be an indeterminate limit, but not necessarily one that does not exist. It just may not be determinable in this particular form. So if the bottom is going to 0, the top must also be going to 0 for the overall limit to exist. So what if we said, I'm going to put therefore the numerator of my expression must be going towards 0. A nicer way of saying that that's a little bit more proper is to say the limit as h approaches 0 of the numerator, that limit must be equal to 0. Okay? I'm going to go ahead and break this up into two limits. It's the limit of a difference is the same as the difference of the individual limits. So I could say the limit as h approaches 0 of f of a plus h minus the limit as h approaches 0 of f of a has to be equal to 0. All right, that looks fine. Think about f of a for a moment. A is a particular number. You plug it into f as long as that's defined, and it is because this original limit had to exist, so everything in this expression had to be defined. This is a constant. It's just some number, so that's a constant. And what's the limit of any constant? That was one of our limit laws. We said the limit of any constant is that constant. So as h approaches 0, another way to think about it is there are no h's in here at all, so this expression is unaffected by h approaching 0, and the limit of a constant is that constant. So this limit right here is actually just f of a. So I now have the limit as h approaches 0 of f of a plus h minus f of a has to be equal to 0. I'm going to move this f of a over to the right side of my equation by just adding it to both sides, and I end up with the limit as h approaches 0 of f of a plus h has to be equal to f of a. Okay, we're going to make one other change here. You notice what I really want to show is this. I want to show f is continuous at a, and we said, what does that mean? That means what I have written right here. It means the limit as x approaches a of f of x is equal to f of a. And what I have down here is looking suspiciously like that. I have an f of a on the right, and I have the limit of f of something on the left. To make it look identical to what I want to show, I'm going to go ahead and use a little substitution. Let's use this substitution. Let's let x, because I notice there's just an x in here, be the same thing as a plus h, because I notice that there is an a plus h right here. If I did that, then this thing inside the parentheses I could rewrite as just an x. So I could use that little substitution to say, well, I'm just going to call a plus h something new. I'm going to call it the letter x. So now I have an x in here. Notice that we're doing a limit as h approaches 0. So what I want you to do is think, well, if this h here is approaching 0, what is happening to x? If h is getting smaller and smaller, you notice that x would be approaching a plus 0. So x would be approaching a. So if h is approaching 0, x must be approaching a. So the limit as h approaches 0 could be replaced with the limit as x gets closer and closer to a. So the limit as h approaches 0 would be the same thing as x getting closer and closer to the number a. And so what do we have? We have this statement that the limit as x approaches a of f of x is equal to f of a. And implied in this statement is that the limit on the left exists and the function on the right is defined at a. So this expression is defined and those two things are equal to each other. This is what we were trying to show up here, because we said f being continuous at x equal a meant the limit as x approaches a of f of x is equal to f of a. This is exactly our shorthand, precise definition of continuity. That's our definition of continuity. Therefore, f is continuous at x equal a. That's precisely the definition of f being continuous at a. So we started out assuming f was differentiable at x equal a. That meant this limit existed. We did a bunch of very technical steps, and we ended up with this statement, which is the exact definition of f being continuous at x equal a. Thus, if f is differentiable at x equal a, f has to automatically be continuous at x equal a. And that's a nice formal proof of this statement, and it's a statement we'll use often in practice and also in proving other theorems. Okay, well, there's one last skill that I want us to learn before we leave this section about tangent lines and rates of change and derivatives. So let's look at the next page. Well, there's one last skill that we want to learn before we leave this section on tangent lines, derivatives, and rates of change. And that is learning more about the relationship between a function and its derivative by looking at the relationship between the graph of a function. You notice here I have y equals f of x and the graph of its derivative. In this particular case, I am not given an equation for f of x. In some of the earlier examples we looked at, for example, at the beginning when we were first learning about derivatives, we looked at the function f of x equals x squared that has some parabola as its graph, and we found the derivative using the limit as h approaches 0 definition of the derivative. We went through a bunch of steps and found that the derivative was equal to 2x. Well, remember that the derivative is a function in its own right. If I wrote this as y equals 2x, I could certainly graph the derivative just like I could graph the original function y equals x squared. But the question becomes, how, if I'm not given the equation of the function, if I'm only given the graph, do I go from that to a graph of its derivative? So here I have y equal f of x, and right down below it, I'm going to try to graph its derivative, f prime of x. Now my graph is going to be something that's sort of a guesstimate. It's going to be a fairly crude graph because I'm getting information just from a rough graph that's been drawn by hand above. But it will help us to understand the relationship between a function and its derivative. Now, remember that down on this graph, if I'm graphing y equals f prime of x, it means that whatever the derivative of this function is at a particular x value becomes the y coordinate of a point on the graph of the derivative. Let's see how that works over here by looking at this table. I have a whole bunch of x values that I'm going to plug in, and I'm going to find f prime of x, and keep in mind that f prime of x is going to become the y coordinate that goes along with any particular x coordinate that I might plug in on this lower graph, the graph of f prime of x. And of course, what is f prime of x in terms of the graph of the original function? Don't forget that f prime of x is simply the slope of the tangent line at that particular x value, and it's the slope of the tangent line on my original y equal f of x graph. So let's look at a particular example. If I have x equal to, say, -5, I look at my original function and I say, okay, well, what I need to do is I need to find the derivative of this function at -5. That means I want to find the slope of the tangent line to the original graph at x equal -5. So I go ahead and I draw the tangent line in here. Let me do it in another color because that's hard to see. So my tangent line looks maybe something like this. And what I do is just estimate what the slope of that line is. It moves up as I move to the right, so it has a positive slope. It looks fairly steep, so maybe the slope of that line might be equal to 4. So I just write that in here. Remember, the slope of the tangent line is the same thing as f prime, so f prime of -5 would be roughly equal to 4, and that becomes the y-coordinate of a point down on my graph of y equals f prime of x. Keep in mind, f prime is the same thing as the slope of the tangent line. So that's a point that I could actually graph down here. In other words, I'm going to be graphing the point -5, comma, +4. That becomes a point down here. -5, +4 would be, let's see, 1, 2, 3, 4, would be a point right about here. That's one point on the graph of my derivative function. Let's go back up here. We'll plug in x equal -4. So here's -4 on my original graph. I go down to my curve, and now I want the slope of the tangent line at this point corresponding to -4, and it's also going to have a positive slope. Will that line have a bigger or smaller slope than the one did over here? It looks like it's slightly smaller. It's still positive, but slightly smaller. Maybe here the slope might be a +3. I go over 1 unit and up 3 units to get to another point on that tangent line. So at -4, it looks like the derivative f prime of -4, same as the slope of the tangent line on the original graph, is roughly equal to 3. And that means the point -4, 3 is going to become a point on the graph of the derivative. So we're using the same x-coordinate, but the y-coordinate on this lower graph is the slope of the tangent line to the upper graph. So at -4, I go up 3 units, 1, 2, 3, so that would be a point that looks like it's right about here. Now we're going to continue this process. When x equals -3 on this upper graph, now I have to go up to hit the black graph, and I draw the tangent line. Still it looks like a positive slope. Maybe the slope is equal to 1 or 1.5, something like that. So when x equals -3, the y-coordinate on my derivative graph is the slope of the tangent line to the upper graph, and the y-coordinate is about -1. When I put in -2, I'm right at this point on the upper graph, graph of f, and that means I have a horizontal tangent line. What's the slope of a horizontal line? Looks like the slope would be equal to 0. So I'm going to say at -2, the slope of my y equals f of x graph is 0, and that means -2, 0 is going to be a point on the graph of the derivative. We continue this process. When I plug in -1, I'm looking at this point on the graph of f. I figure out its slope, and notice that its slope is now going to be something that's negative. As I move along this line to the right, I fall. So the slope of this line will be something that's negative. Maybe that slope is -1. And again, that's just an approximate guess for what the slope of that is. So -1, -1 will be a point on the graph of the derivative. When I choose x equals 0, that's the next value in my list, I draw the tangent line. It looks like it's a slightly steeper line, and so the slope of that line is going to be larger in absolute value, smaller in absolute terms. So the slope of that might be -2. So I'm going to say at 0, it looks like the slope of the tangent line is -2. That becomes the y-coordinate of this point on the graph of the derivative, 0, -2. And now what happens when I go to x equal 1? Well, it looks like I still have a negative slope, but the line has a shallower slant to it, so the slope might be back to -1. I go over 1 and down 1 to find another point on that tangent line. So here perhaps the slope is -1. So I'll graph 1, -1 on here. When I get to 2, I'm looking at this point on the graph of f. What does it look like the slope of the tangent line is there? Well, that looks like it's right at the bottom of that curve. So that to me looks like a horizontal tangent line, meaning now I'm at a slope of 0. So I'm going to plot 2 comma the slope here. So it's the same x coordinate, but the y coordinate is whatever the slope of the tangent line is up here. Okay, and when I put in x equals 3, notice that I'm back to a positive slope for my tangent line. Maybe here my slope might be equal to 1 over 1 up 1. So I'm going to graph 3, 1. And again, notice that I've lined these graphs right up underneath each other. So at the same x-coordinate of 3, I'm just going up to a y value that's the same as the slope of the tangent line, whatever number I have for the slope on this graph. When x equals 4, I still have a tangent line that looks like it has a positive slope, but it's steeper. So I don't know, maybe the slope of this line is equal to 3. And again, I'm just eyeballing it. So when x equals 4, I go up 3 units on the y scale here because the slope of this tangent line is 3 on the graph right above it. And at x equals 5, what do you think the slope might be at this point? Well, if I draw the tangent line, it's still a positive slope. It's even steeper than this one. Maybe the slope is 4, 4.5, 5, something like that. So I'll put 4 as a guess for the slope of the tangent line there. So at x equals 5, my y-coordinate is the slope on the curve that's above. So I go up to a value of roughly 4, and that will be a point on the graph of my derivative. Now I can see that the slopes of the tangent lines change in a smooth and continuous way as I move along here. So I'm going to assume that this is a nice continuous curve without any super abrupt changes, no sudden jags or anything like that. So I'm guessing that this is a fairly smooth curve, and I'm going to go ahead and say that it has to be continuous. And it won't be too pointed down here because it will also be fairly smooth because this curve has a nice smooth curve to it. So the tangent line slope is going to be changing in a continuous and gradual way as I go along. But this would be a rough sketch of f prime of x, the derivative of the function that's above. And just keep in mind that wherever the slope of the tangent line to f is positive, the derivatives graph must be above the x-axis because your y-coordinate is the slope of the tangent line, and you're saying that your y-coordinates are all positive, as opposed to places where the slopes of the tangent lines are negative. You see from -2 to +2, the slopes are all negative. So from -2 to +2, the graph of the derivative is below the x-axis, and that's because the y-coordinates are the slopes of the tangent lines, and all of these points have to have y-coordinates that are negative. Notice that when we get past 2, the slopes of the tangent lines are positive again, and now my graph is above the x-axis, and that again is because the y-coordinate is equal to the number of the slope of the tangent line, and those numbers are now positive. So my points have to have positive y-coordinates, and they must be above the x-axis. So in here we have negative slopes of tangent lines on the graph of y equal f of x, the graph that's above. And for these green sections, when x is less than -2 or greater than +2, we have positive slopes for the slope of the tangent line to the original graph. Okay, let's go ahead and look at another example, and I'm going to have you try to figure out how to draw the graph of the derivative given the graph of the original function. And this one is a little bit different than the one that we just talked about. It does have some sharp changes in the slopes of the tangent lines. So one way to do this is just to go through and pick out certain x values. You might choose x equals 0. Think about what happens between 0 and 5. So you might try something like x equals 3, say. Then think about what happens between 5 and 10. You might try something like x equals 7 in there. Then think about what happens between 10 and 15. Maybe consider the x value 12, something like that. And keep going through here and putting in different x values. Figure out what the slope of the tangent line is to the y equal f of x curve. And remember that down here, y is the derivative of whatever particular x value you're looking at, and that's the same as the slope of the tangent line, the number that you get for the slope of the tangent line on the curve that's above. So try pausing the video and see if you can come up with a graph. And again, it will be a rough graph because you're really guessing at what some of these slopes are of the derivative of the function that's graphed above. And then restart the video and we'll go through it together. Okay, let's go ahead and try this together. First of all, I want us to think about what's happening between 0 and 5. And you notice that at an x value such as x equals 3, if I were to draw the tangent line to this graph at that point, since it's a straight chunk of graph, in other words, it's a straight line for that little section there, the tangent line would actually lie right on top of my curve. That's the line that follows the curve as closely as any straight line can. It's right on top of the curve because the curve is actually a straight line, at least for this little section between 0 and 5. And what's the slope of that line? Well, it appears to be a positive slope. It looks like it's slanted at about 45 degrees. So if I go over 1 unit, I will go up 1 unit. So maybe the slope is equal to 1. And notice that that would be true for every point between 0 and 5. And if this arrow is indicating that this continues in this direction forever, then actually it would be true for all x values less than 5. So for all of these values, x less than 5, the slope of my tangent line is 1. That means when I come down here at each x value, such as x equals 3, remember the y-coordinate is whatever number we got for the slope up here. So if I kind of connect these graphs together, I go over to the x value that I have here, 3, and the amount that I go up, the y-coordinate of my point, is supposed to be the slope of the tangent line. And we said that slope is equal to 1. So 3, 1 would be a point on the graph of the derivative. And because all of these points to the left of 5 have a slope of 1, it means if I choose another x value, such as x equals 0, the slope of the tangent line is still 1. And so I would still go up to a height of 1 on the y-axis for the graph of f prime of 0. And that would be true for all these values. So actually all of them have a slope of 1, meaning that I would want to go up to 1 on the y-axis for all of these points up to x equals 5. What does it mean about the graph then of y equals f prime of x? Well, to the left of 5, I'm actually going to get a horizontal line that crosses the y-axis at the value 1. And if this continues forever in this direction, all of the slopes of the tangent lines will be 1, and so I keep getting 1 as the y-coordinate for all of these points. Okay, let's think about what happens at 5. Now at 5, you notice that what we have is a corner. And what did we say about f prime of x when we're at a corner on the graph of y equal f of x? Remember we said that is a point where we have trouble. It's a place where there's a sudden sharp change in the slope of the tangent line, or sometimes intuitively we simply say there's no unique tangent line that you could draw right at that pointy part. So because there's a corner, it means that the derivative does not exist there. F prime of 5 doesn't exist or is undefined. So there is no derivative right at this point. And how would I express that down here? We're saying when we put an input of 5 into this function, the y-coordinate doesn't exist. There is no slope of the tangent line there. The function is undefined. F prime is undefined at 5. And the only way to show that graphically is to put a little hole in the graph. What that means is when I try to find the output of this f prime function, I can't find it. There's just a hole in the graph right at that point. Okay, let's move on to this section between 5 and 10. You could think of something like the x value of 7. I go up to my graph and I ask, what does the tangent line look like at 7? Well, at 7, because we're looking at a straight piece of graph, the tangent line again is going to lie right on top of the black graph. It's a line that has a negative slope, and maybe the slope is roughly equal to -1. And that would actually be true for all x values between 5 and 10 because we're right along a straight chunk of graph. So when I put 7 into this derivative function, my output value, my y value, is supposed to be -1. So the point 7, -1, is a point on my graph. But the same would be true for all these x values between 5 and 10. If I choose this x value of 9, same thing is true. The slope of the tangent line would still be -1 because the tangent line lies right on top of the black graph. So at 9, we also have a y value of -1 on the graph of the derivative. And that would be true for every x value in between 5 and 10. And so you're going to get another horizontal line in this section. Right at 5, we said the derivative is undefined. So I have to put a hole in the graph here to indicate that my derivative is undefined at 5. And you notice at 10, there's also a sharp change in the slope of the tangent line. And so I also have a point at 10 where I have kind of a corner or a sharp change in the tangent line, and f prime of 10 is also something that is undefined. So at 10, I have to also put an open circle here to indicate the idea that my derivative is not defined at 10, so this function has no output value at 10. But everywhere in between, for all points in between, the output value is -1 because the slopes of the tangent lines of all of these points from 5 to 10 would be a slope of -1. Okay, great. So we've drawn this part of the graph. If you had trouble doing this part, you might want to pause the tape again and give this section another try. And then we'll go ahead and go through it together. Okay, so now let's concentrate on the part between 10 and 15. If I choose an x value such as x equal 12 and I draw the tangent line, it's actually going to be a line that lies right on top of my black function. And again, that's because the black function is actually a straight line through that section from 10 up to 15. And it looks furthermore as if it is a horizontal tangent line. Well, what's the slope of a horizontal line? The slope would be equal to 0. And that would be true for every x value between 10 and 15. So the y-coordinate corresponding to x equal 12 would be whatever the slope of the tangent line is on the graph above it at that point, and we said that slope is 0. So 12, 0 is a point on the graph of f prime. And that would be true, we said, for every x value from 10 to 15, all of the tangent lines are horizontal, so we have a bunch of m equals zeros up here. And so all of these x values would have a corresponding y value of 0 from 10 to 15. Now at 10, we said f prime of 10 is undefined because you have a sudden change in the slope of the tangent line. It goes from -1 suddenly to 0, and that means that f prime of 10 is undefined. We have to indicate that somehow on our graph of f prime, and again we indicate that by putting an open circle right at 10. But everywhere from 10 to 15, we would have an output value of 0, and so we just get a little horizontal line of values from 10 up to 15. Now what happens at 15? Is there a sudden change in the slope of the tangent line right at 15? Well, it looks to me as if there isn't a corner here, but that the tangent lines just start to change slowly. There's 0 just to the left of 15. Maybe it's still 0 right at 15, but as I move a little bit to the right of 15, say to an x value of 16, it looks like the tangent line has changed in a gradual way to be a slightly positive slope. Maybe here the slope might be something like 1/2. And as I continue to move to the right, say I choose the x value 18, it looks like the slope of the tangent line is getting steeper. Maybe here the slope might be equal to 1. When I get to 20, perhaps the slope of the tangent line is equal to 2. I go over 1 and have a rise of 2. And what happens as I continue past 20, it looks like the slopes of the tangent lines are getting steeper. So maybe I have a slope of, I don't know, 4, something like that, when I get to the value x equal 22. And then we'll talk about what happens after that point in a moment. So let's start to graph some of these things down here. I have a slope of 0 at 15, and then the slope becomes 1/2 when I get to 16. So I'm going to put x equals 16, and the corresponding y coordinate is 1/2 unit. So I go up 1/2 unit. And when I got to 18, I said it looked like the slope of the tangent line was roughly equal to 1. So at 18, I'm going to go up to a y coordinate of 1 on my derivative graph. At 20, maybe the slope is equal to 2, so I'm going to go up to 2. So 20 comma 2 is going to be a point on the graph of the derivative. And at 22, we said it looked like the slope might be as high as 4. So I'm going to go up to 1, 2, 3, 4, maybe right here. So since it looks like the slopes of the tangent lines are changing in a gradual, smooth way, I'm going to try to draw a nice continuous curve through this section. Looks something like this. Here's 1/2, here's 1, here's 2, and here's a height of 4. Now, let's think about what happens past 22. If I looked at something like x equal 24, for example, looks like I still have a tangent line that has a positive slope, but is it smaller or larger than the 4? Looks like right around 22 I may get to my maximum slope of my tangent line, and when I get to 24 the slope is still positive but a smaller number. Maybe I only go over 1 and up 2 units at that point. So at 24 I still have a positive slope for my tangent line, but it is coming down and is maybe a value of 2 again. So what I drew right here is maybe not quite correct. This looks like it is at the maximum. Here's the maximum slope of the tangent line on this graph. Looks like it occurs at about x equal 22. So my derivative graph will go up, and then the slopes start leveling out and getting smaller. So I'm going to have y values that are again decreasing, that are getting smaller. So the slopes are increasing in value till I get to this point, and then they are still positive but are decreasing in value. So we show that over here. The y coordinates are getting larger. We get to some maximum slope of about 4, and then the slopes start coming down again, 3.5, 3, and now I'm down to a slope of 2. Okay, what happens at 25? If I draw the tangent line, you notice that it's going to be horizontal. That means the slope at 25 is going to be back to 0. So when I get back to 25, this slope is back down to a value of 0. And what happens after 25? If I plug in something like 27, can you tell me about the sign of the slope of the tangent line there? It's a line that moves down as we move to the right, so its slope is negative. Maybe the slope is equal to -2, something like that. So at 27, my slopes have become negative, and the point 27 comma -2 is going to be a point on the graph of the derivative. So remember that at each x value on this lower graph, the y-coordinate on the lower graph is whatever number the slope is on the upper graph, and that number has become negative. And it looks like beyond that, the slopes continue to be negative, but steeper and steeper. Here maybe the slope is -4. Here maybe the slope is -6. So when I pick something like, say, 28, it looks like the slope might be -4, so I have to go down to -4 on my graph for my y-coordinate. At, I don't know, 29, the slope might be -6, so 29, -6 is a point on the graph of the derivative. And at 30, it looks like you have a very steep tangent line. Maybe the slope is equal to -10 by the time you get to 30. So 30, -10, which is almost off my graph, would be another point on the graph of the derivative. And we just continue to connect these dots together in a kind of a smooth and continuous way. And very roughly, at least, I've drawn a graph of f prime of x, only knowing the graph, not the equation, of f of x. Okay, well, this concludes our discussion of tangent lines, derivatives, and rates of change. And in the following videos, you will see an explanation of how to find derivatives in a quicker, faster way than using our original definition, the limit as h goes to 0 of f of x plus h minus f of x all divided by h. So that's what we'll be looking at in the next sections.